All right, so remember that a free body diagram is simply a diagram, and it shows all the various forces that are acting on the object. And the word free just means that it's free from all its surroundings. We sort of draw it very, very simplistic. In fact, we'd simply draw, usually, a box, and it doesn't matter what shape it is, right? So here we have a book resting at rest on a tabletop, diagram the forces acting in the book. We learned yesterday that most things happen on Earth, and so we have a weight force, right? Force of gravity down. And because it's sitting on a tabletop, action, reaction, there's another force which is upward. And what do we call it? Normal force, Fn. Are those balanced, Kaylee? Are they supposed to be?
Yes.
Yes, because the object is not accelerating up or down, right? It's just sitting there. So those forces are balanced. And you will recall yesterday that I said some people believe you should not do this because that's not part of the free body diagram. It's sort of extra. Jimmy cracked corn, I don't really care. You know, Jimmy cracked corn and I don't care. He can crack his corn if he wants, I don't care. In fact, I don't even know what cracking corn is, so like, who cares?
One day, I'll search it up.
You lay there. A girl is suspended motionless from a bar which hangs from the ceiling by two ropes. Diagram the forces acting on the girl. So many of you probably did this. Now, how many people put one force? How many people put two? Oh, lots of you. Well done. So yes, technically you should have, yeah, FT, and I'm going to draw two individual ones here. And they should add up to what? They should be, yeah, they should sort of add up to that, right? If you just put one, that's okay. I don't really get too excited about that. Having said that, though, if there are different directions, do you need more than one? Like if one was up and one was to the right, you can't just not do one, right? Okay, so it's not a terrible habit to get into for every force there is. For every contact point, I guess, have another arrow. Does that make sense? Okay, good. Okay, egg is free falling from a nest in a tree. Neglect air resistance, which means don't worry about it. Diagram the forces on the egg. So we have gravity. Anything else? Nothing else. Right? It's just free falling, gravity. There's no left or right. Yeah, yeah. Sing it if you want to. Actually pleases me that you guys know that song. Yeah. It's possible. Really? Oh. We'll just put like a big poster of Bodhi. No? Yeah. Things change, things evolve. A flying squirrel is gliding, no wing flaps, from a tree to the ground at constant velocity. Consider air resistance, diagram the forces acting on the squirrel. Okay, so weight force again. When we say constant velocity, what does that imply? What does that mean? What is that? No acceleration. What about the forces? Equal. The forces are equal. So we got to have two forces that are equal here. So what's the opposing force? It's not a normal force. It's not sitting on something. It's a friction force or it's a air resistance. I usually put F air, fair, yeah, but the label, the subscript is simply a label for the type of force it is, right? Now there's always been some kids that argue over the years that the squirrel is moving to the right, and so therefore there should be like, a little bit of air resistance this way. I'll gladly accept that. But if you do that, then realize that is the velocity constant now? No. Because the forces aren't balanced anymore, are they? Right? So I really should probably change this question so that it says, instead of gliding, I should say it's falling at a constant rate, right? Yeah. Although it makes for a good conversation. A rightward force is applied to a book in order to move it across the desk with rightward acceleration. Consider frictional forces and neglect air resistance. Diagram the forces. Weight force, it's on a desk. Normal force. Rightward acceleration, consider friction. We always usually show things go, it says rightward, I guess, actually. So I got friction like that, and because it's accelerating, I have a large applied force, FA, applied force. Clearly larger than the friction force. Right? Number 6, is it any different? What's different in number 6? Constant velocity. So here, the friction force and the applied force are the same length. They're the same length. So far, reasonably easy, right? College student rests a backpack upon his shoulder. The pack is suspended motionless by one strap from one shoulder. Diagram the vertical forces. Weight force. Is there going to be one without a weight force?
No.
It's one strap, FT, or I would accept FA too, right? Balanced? Yeah, because it's motionless. Skydiver descending with constant velocity. This is basically the same as the squirrel. Weight force. Air resistance. When you jump out of a plane, do you accelerate?
Yes.
You do, and then eventually you reach, do you guys know what that's called?
Terminal velocity.
Terminal velocity. And that is when the gravity down is equal to the
Gravity up.
air resistance up there. More on that a little bit later.
Gravity up.
Yeah, you just keep going at the same rate. Yeah. Your velocity has reached a terminal, right? It's yeah, the end of the velocity. As you get closer to the ground? No, there'd be more actually, because the ground actually gets thicker. You would actually slow down a bit. Yeah. You'd reach a new terminal velocity. A force is applied to the right to drag a sled across loosely packed snow. Loosely packed snow is code for friction. Weight force, normal force, rightward acceleration. So we've got leftward friction, applied force. Okay, now the next one usually causes some discussion, some discomfort. Discomfort. A football is moving upward towards its peak after having been booted by the punter. Neglect air resistance, diagram the forces. So, football is played on earth. Weight force. Anything else? Has it left his foot already? I'm assuming it's a male punter. Has it left the punter's foot? How is he applying a force to it? FBDs only show forces. They do not show motion. Objects in motion stay in motion. The ball keeps going, right? The only force acting on it is gravity. Always causes some discussion. Yes. If there was some air resistance, if it's moving upwards, then I guess it would actually be like this, wouldn't it? Right? You can't tell the direction of the motion. Right? It doesn't show motion. It only shows forces. Okay? So yeah, people always get a little bugaboo there. Car is coasting to the right and slowing down. So we got the weight force down, we got the normal force up. It's coasting to the right. Now, how do you interpret that? What does that mean? Going slower, but braking? Foot on the gas? Just coasting. So what's causing it to slow down? Friction. Okay? Coasting. Are the forces balanced then now?
No.
Yeah? What does balance mean? You don't know what balance means? Like if you got 5 on this side, you have to have 5 on this side, right? So like these guys are balanced, right? Like I got minus 10 and plus 10, but is there one balancing this one? These forces are unbalanced. There's a net force, therefore there's an acceleration. What were you going to say? It's not going at a constant velocity, slowing down. Okay, is that good? Yeah? Okay. We're going to use Fnet is equal to MA, and we're going to use Fnet is equal to FA plus FF, plus all of the kinematics questions that we learned last unit. Jaden, put it away and watch. Okay. Remember, one of the good strategies for doing this is writing down what you know. And if you're past this stage, that's fine. A constant force acts on a 12 kilogram mass. M equals 12, right? Changes its velocity from 4 to 18. The velocity is changing. So that means we have an initial and we have a final. What is the initial? 4. And the final is 18. And this is all happening in 3.5 seconds. And the question is, what is the force? What is the applied force, I guess, right? How much force is being applied to do this? Okay, well, the only one with FA in it is this one, right? Do we have any friction? No. Does that mean that the FF is 0?
Yeah.
It does. It's not mentioned, right? So we're going to assume. So in other words, that disappears. So in other words, Fnet is equal to FA. So once I got Fnet, I know what FA is. How do I find Fnet? M times A. Do I have A? A is equal to, don't write this down. A is equal to, do I have the change in velocity and the change in time? Got the time, do I have the delta V?
No.
Move it over.
Oh, right.
Delta V is equal to VF minus VI. There's our start. You got to kind of do that backwards thinking. Delta V is equal to VF minus VI. The VF is, the VI is 14, right? Now what do I do with that? Put it over here into the next one. Delta V is 14, the time is 3.5. Taylor, are you getting this down? So, what's our acceleration? Did you guys work it out? It's 4, that's right. Okay, now that I've got that, what am I going to do? Now I'm going to go Fnet is equal to MA. The mass was 12. The acceleration is 4, which makes the net force 48. And we already sort of predetermined that the net force is equal to the FA, right? Because there's no friction. Therefore, the FA is 48 newtons. Should I have drawn a free body diagram for this, maybe? An FBD, should I have drawn a diagram for it? It doesn't ask for it. If you had to, I guess it would look like this, right? Weight force, normal force, FA. Are the FW and the FN, are they part of the question? Do they do anything? Like, do they make any difference at all? They don't. So all you really got is that FA. So really, I mean, the diagram, it might help some people, but is it really integral to this question? Not really. Although it's not a terrible idea to get into the half a drawn. I would say likely 1, 2, 3, 4 marks, and maybe a 5th one if I ask for that. Do you see how writing the formula, lining them up, putting them in little steps is helpful? Yeah. You've graduated, you've moved past the one-step questions where it's just, do I times them? to a 3-step problem, okay? And it's going to get bigger and bigger and bigger. F net. Over here, Kelly? F net. Okay, I think this one you're missing the picture, right? Yeah. So we've got a 2-kilogram block being pulled by a rope as shown. We got 25 newtons of force are being applied, and the friction force is 5.
That doesn't have the 2 kilograms.
Oh yeah, that's right. I forgot this morning. I had to add in the amount. So you got to write in the 2 kilograms, right? I changed it up here for the next class, but your paper was already run off. So add that in. Drawing the diagram. Now this would be the applied force, right? And this one here would be the. And is there a weight force and a normal force? Yeah, but once again, doesn't really do anything, right? They're balanced. Okay, what do we know? We know the mass is 2. We know the FA is 25. We know the friction is, now it's 5, but because it's to the left, -5, right? And I'm asked to find acceleration. Well, A is equal to delta V over delta T, but I don't have a velocity and I don't have time here, do I? So that's not going to work. What's the other one that has A in it? F net is equal to ma. I have the mass. Do I have the net force? No. But I can figure that out because the net force is simply the sum of all of the forces. So let's start with that. FA plus FF. The applied force is 25. I'm going to write it as plus minus 5. Is that okay? Which, of course, is 20 newtons. The net force is 20. Again, notice how I'm writing out the formula. Even though I know how to do these, and I could just do it with a calculator, right? I'm showing you this is the way I want to see them. I'm showing you my knowledge. F net is equal to 20. Now I'm going to write F net is equal to ma. (20) is equal to the mass, which is 2, and the acceleration. How do you solve? Divide by 2. Acceleration is 10, right? Okay, so part B is a little bit different. Part B says if the force applied for 4 seconds, determine the velocity. They mean the velocity at the end of 4 seconds. The end of that interval, the final velocity. Will this work? No, but we're going to solve for that. Right? We're going to have 10 is equal to the change in velocity, because the change in velocity is certainly related to the final. This is 4 seconds, so my velocity changes by, multiply both sides by 4, right? You got to divide by 4, we're going to multiply by 4. So that's going to be 40 meters per second. Did it say anything, Noah, about what the initial velocity was? It has to be. If it's not given to you, it has to be 0. And if the VI is 0, then the change in the velocity is the same as the final, right? I mean, if you want, you can write it out if you want. As long as you sort of indicate you know that this is not this, you have to turn this into VF. As long as you at least state VF is 40. Are you starting to see why I want the formulas written? I hope. Yeah. What do you say here? 1, 2, 3, 4. Ready to try one on your own? No? Yes? Oh. Is this one different?
Yes, being pulled in 2 directions.
2 directions, not just left and right or up and down, but south and east. Okay, maybe I better do this one. I should let you know too that there's don't write this down. There's 2 types of situations. There's ones where you're sort of looking at it from the side, but something like this when it's south and east, what's your viewpoint here? Top down, like from a drone, right? Bird's eye view, they call it. Right? Is that what this one is? Yeah, okay. So we got south and we got east. So south, 250. East, 150. Now, those are 2 different applied forces. What might be an appropriate way to label those 2 forces? How about like F1 and F2? Would that be okay? Now, how do you add those forces? Remember our old friends vectors?
Oh, my help. Way to go. Oh, God. What is that?
Physics is like Shrek.
Please don't. I like Shrek. I like Shrek. Is it always...
Go ahead, Teague. Why is it like Shrek?
Because that's layers.
Has layers. We just like onions and parfaits. We keep coming back to things over and over. There's no need for redos because we keep doing over and over. I asked my morning class if they would like me to do physics with my Shrek mask on, and they said no, that'd be creepy. Yes, I understand. Yeah?
Yeah, you should do it. Do it on Monday. That would be my
Okay, so F1 and F2. Now, when I add these together, I'm going to get this kind of thing, right? And that's, if there was no friction, that's the direction that it would go, right? So what am I going to call that? Well, I'm going to say F1 and F2 combined together to give you, is that okay to call that FA, do you think? That's kind of like the overall applied force? Yeah, I would draw that. That's the overall applied force, right? So we're going to call the individual forces 1 and 2, and we're going to call the sum of those FA. Now, is that the overall net force? We still got to do, well, yeah, but we still got friction involved, right? I'll get to that in a second. So how do I find my FA? Did I conveniently make them perpendicular to each other? I did. So FA squared is going to equal F1 squared plus F2 squared. So FA squared is equal to, I guess that's going to be 150 squared plus 250. Does it matter which one you label 1 and 2? So 150 squared plus 250 squared, and then make sure you take the square root, right? $291.5? That sounds familiar. Getting this down, Braden? Okay. 291.5 is what I got. Does that make sense? Like, should it be a little bit more than 150 and a little bit more than 250?
Yeah.
It's a hypotenuse, right? 291.5? Okay. No, you're not fooling anybody by hiding it under the desk.
What's the units? Minutes? What's the units?
Newtons.
No, like for the, oh, it's force.
Yeah. Okay, now is that the net force?
No. No.
Take the square root. Yeah. Okay, which direction is friction? Friction is always opposite the motion. If there was no friction, which way would it go? This way, right? So that means that our friction is actually that way, isn't it? Right? Now, the net force is the applied force plus the friction force. And the applied force is that 291.5. And we're going to add, now can we just go minus 50? Can we do this? Even though we don't know what angle those are at? Well, we know that the friction force is exactly opposite the applied force. So yes, we basically assign that direction to be positive and this direction to be negative. So you can just do that subtraction. So 291.5 minus 50 is 241.5. Now that just gives me the F net. Now if I want acceleration, I'm going to have to go divide by both sides by 100. Right? F net is equal to MA. 241.5 is equal to 100. That's the mass. Divide by 100 and you get 2.4 meters per second squared. How do you feel about that? Here, generally we make the friction negative. Yeah. Ready to try one? I made sure that the next one is easier. Here's what I want you to do. I think I left you quite a bit of room, right?
Yeah.
Okay. I will help you out. It is a two-step question. It's kind of like a country question. It's two-step. I would suggest you draw a line down the middle and you put your answer over here. And I'm going to do the example over here. And if you get it wrong, well, then you got the right answer. And if you get it right, well, then no problem. I'm going to go do my attendance. You guys try number 4. What you've done, what the vast majority you've done is entirely normal. And I do this on purpose. Because the mistakes you make, usually, actually you guys did a really good job. I saw everyone writing the formula. You made one tiny mistake. Let me show you. Almost everyone that got started did this. You know the mass, you know the acceleration. So you can get the F net, right? Because you know the mass, you know the acceleration, so it's 1,800 times 1.75, 3150, I think, right?
Yeah.
Okay, now here's what the classic student does. They just say, oh, subtract friction, because that's what I always do. Wrong, wrong, wrong. Write the formula. And as I said, you guys did a really good job. I was pleased to see that. Most people that I saw that got this far wrote F net is equal to FA plus FF. The net force is 3150. Put it in the right spot. Assign that variable to that number, computer science people. What is the applied force? What I'm solving for. But the problem is the friction force is minus 250.
That's one of my questions.
And so when it goes to the other side, it becomes plus 250. And so the FA is 3150 plus 250. Right? Because this line becomes 3150 is equal to FA minus 250. And how do you get rid of minus 250? You add it to both sides. You add it to both sides. Just like when you're doing this, right? Hang on. That's not what I wanted. 10 equals x minus 2. What's the answer? 12 minus 2 is 10. How do you get rid of minus 2? Add 2 to both sides. You guys have done this. It's the same thing, exactly the same, just little bigger numbers, and it's not an x, it's an FA. Same thing. So FA is equal to 3150 plus 250. The correct answer is 3,400 newtons. And if you stop and you think about it, does the applied force have to be more to overcome friction?
Yes.
Yeah, right? Like if you need 3150 just to accelerate it, you need 3150 for the acceleration, and you need another 250 for friction. You need more. How do you make a car more fuel efficient? Reduce the drag, reduce friction, make it more aerodynamic, right? Little Ferraris are good on gas, sort of, because they're low and they're aerodynamic. Big semis, not so good. They push on air. Yeah. Okay. You don't have the secrets. Let's go. Give me 30 more seconds. Hang in. I know you guys have been sitting for a while. I get that. Okay, here it is. I prepared a bunch of practice questions for you. The first side is called Newton's Law Problem Set 1. Guess what the next side is called? Set 2. Now, there are answers at the bottom. There's a QR code for both sides. It's all one set of solutions. There are some problems you can't do yet. Okay? They're trying to mix it a little. I need to start separating my. It takes a huge amount of time. But there will be some questions that you can't do. Like, for example, number 7 and number 8. You see what I have in italics there? Force at an angle. Have we done any forces at angles yet? Yeah, a little bit, right? Don't do 7 and 8 yet. Don't do 7 and 8, and don't do 2. I guess it's 2. Okay? Now that doesn't mean you have to do them all, but you should do, you got a long weekend here, you should do at least one side. Okay? You've got about 20 minutes here. Do as much as you can now. Why? Because I'm here and you just learned it. Okay? The magnitude is just the amount of the force, the size of the force. Okay? The answers are also available up here in the red binder. I think it's red. Is your guys red?
I have no clue.
Right here. Okay, so your answers are here in the red binder. I'll open it up to the right spot. Use this time wisely. This will save you time later. It will. Now you can go for those.
I go back.
Sure. Someone's leaving me too.
I don't know, man. They take all that time and then